Hi, and welcome Math 212 students. We're looking at section 7.2 today. What we're going to do today is look at two sets of data using scatter plots, box plots. We are going to be looking at standard deviation, the normal, and maybe a little bit of inferential statistics, basically just explaining what it is. So here we are going to look at comparing two sets of data. We want to figure out maybe, I think in your textbook it was the front seat legroom and the rear seat legroom for different models of cars, what that looks like. Here we're going to look at the peanuts question again, basically. Let's look at that. Oops. Oh, this is a button I'm supposed to push. So let's look at that. How many more peanuts can adults hold than children? Boxplot is a really good one for this. You can do that on your calculator, and I have directions in my instructor notes. Let's look at it, though. I just went to Desmos and looked at their boxplot. You can also look at their scatterplot calculator. I think I cut myself off. Hold on. Getting ready to go to that website. Okay, I keyed in the numbers for the children, and there were 22 elements in that list. I just keyed them in. Let's see, we can look at those. See if we go all the way back through here, we can see that I've entered those in, and that's what it looks like. I just went in there. I went to desmos.com and I asked for a boxplot generator, and they had the syntax all set up for me, and all I had to do was just enter in my data, and it created my boxplot for me. You can watch as if I erase this number, you can see that it will just adjust it for me, and it will change to have an, oops, I didn't do all of them. It will change it to have a new value. So let me put that one back in there, because I would like to snip this and put it on our slide and compare the two. Okay, if you go through my instructor notes, you'll see that you can enter this data into your calculator, and you can ask your calculator to break this up into quartiles. And the very center here, whoops, that's not what I wanted. Okay. Go back to my pen. All right, which it did not do. Pen. Okay, so the very center here is the median, and then you have your different quartiles. Notice that my data for the college students ranges from 18 to 37, so you get the whole spread here. And then this would be your quartile 1 and quartile 3, and our center there being the median. So we can see how this data stacks up. Notice that I have a big range, and looks like we have some college students that can really grab a bunch of peanuts. So what kind of statements can we make? Well, we can make statements about, look at how the spread of data for the college students is very large, and it goes over that entire 18 to 37, so that's a spread of almost 20. So that's quite a bit larger than the spread here of the children, with a spread of about 14. All kinds of different things we could look at. We could talk about the median there being 25 for college students. We can just look right at the graph. Rather than looking at the sets of data, I can look at the graphs and know what the median is, what the spread is, and how this data is broken apart. Now on to standard deviation. Now you'll see that the mean absolute deviation is just going to be how each of your data points varies from the mean, and then standard deviation itself, usually that's not taught until high school, but we can look at how that data is spread out, and we can see how the data are represented. So in this, we're talking about the mean, median, mode, or the sense of the middle of the data. The standard deviation tells us how that data is spread. We're going to look at this more carefully and in depth, and I kept trying to avoid saying a normal because here we are going to talk about the normal. And this really does let me know how the data is spread, the normal distribution. So let's look at a couple of different graphs here. We've collected some data on the heights of the college students at a college. We can see we've collected that data, and I'm not really even sure if it's in, well, it wouldn't be an inch. I don't know what that measurement is. Let's think about it. Oh, I see what it is. This is actually in inches. The inches are down here on the bottom. They didn't label this graph, which I believe that they should have. The inches are in the bottom, and this on the left would be how many of those students were that particular height. Okay, it's nice to have labels on these graphs. So I'll write number. Oops, I don't want an eraser. Number of students. So if I look at this, I could see that 40 students were about 68 inches tall, or 5'8". And I had 10 students that were about 61 inches tall. Looks like maybe 14 of them were 5'2". That's how that goes. Now, this is the actual data because you could see them in chunks, but when we draw these, we tend to draw a smooth curve because we say we are going to ask a bunch of people and not just, however many it is they ask. They might have asked a couple hundred. Oh, here's where they tell me what these graphs represent. The heights have been measured in inches, and the left is the true depiction of data, and here it is me just making a smooth curve out of it. You're going to see a lot of different data that are represented by the normal curve. One of those that you may see quite a bit would be IQ tests. IQ tests and SAT scores, different standardized tests that you give students fall in that bell-shaped curve. So those students that are getting those state exams, if that's going to happen to you in your classroom, you will tend to have a bell-shaped curve to your test scores. So let's look at what this one is talking about. Here is a normal curve, and if you gather enough data, we say that, well, let me explain this curve first. We would say that in the very center would be the mean. So the mean is 250. And the standard deviation is 50. So this is one standard deviation. This is two standard deviations. And they could either be above or below the mean, but this is also one standard deviation. So since the standard deviation is 50, all these normal curves you can just put the mean in the middle and then go to either side. So it'd be 50, so that'd be 300. This would be 350. This would be 400, 200, 150, and 100. All right, so let's say we have a standardized test. How many students would I expect to score over 350? So all of these students, both here and here, are scoring over 350. So I would expect 2.14 plus 0.13, 2.27%. So 2.27% would score over 350. How many students would I expect to score at least 200? At least 200 means from Unless you get a different color pen. So let's go for, let's go ink color. How about blue? So 200, that would be from here on. So this answer to this question is I would add up 34.13 plus 34.13 plus 13.59 plus 2.14 plus 0.13%. And whatever that adds up to, that is what I would get. These are all in percent. So you just add up all of those percentages, and whatever that is would be the number of students that I would expect to score over a 200. So let's look at our next slide. More normal curve stuff. So let's play again. The average tire is 44,000. So in the middle, we have 44,000 for our mean. Here are our different standard deviation, 1, 2, and 3 standard deviations. Distribution, standard deviation is 2,500 miles. Okay, so I have to add 44,000 and 2,500. So it looks like that would be 46500. I'm going to add those up and write those in for you. I wish they'd give me a little better numbers, but we'll take those numbers. Let's see, my pen went away. Pen. Okay. So a company guarantees that a tire will last 39,000 miles. What percent of tires are likely to wear out before the 39,000 miles? So that would be from these guys right here are not going to last the 39,000 miles. So that would just be the 2.14 plus 0.13, 2.27%. So only 2.27% are likely to get that refund. Next, we have scatter plots. In these scatter plots, we're going to look at these relationships and see what's going on, see if we have a relationship. In this graph here, the ages and heights of group of elementary school. I'm glad they put stuff on the graph here so we can see what's going on. The bottom we have ages versus height. Nice. How would I describe the shape of the graph? Oh, let's see. It looks like if we had 2 students that were 6 and they were right at 40 inches tall each. We have 3 students that were 7 and they were kind of spread out in height, especially this little guy here. He's a tiny guy right there. That's a tiny one there. And then we have 3 students that are 8, and here's how their heights range. We have 4 students that were 9, 3 that were 10. And it looks like to me I have a pretty strong relationship between your age and the fact that you're getting taller. In fact, I could almost draw a straight line through there, and I think it will kind of keep increasing until a certain age. So that would be, that's all they gave for me for that. So how would I describe the shape of the graph? I think it's going to be linear. I figured they would have me something else here. But so yeah, I think there's a strong correlation between the height and your age if you're a child and it's going up. So now we have a bungee jump, and students are modeling that with a rubber band and some weights, seeing what goes on with that. So let's look at what goes on. We put a number of weights on, and then we saw how long the rubber band stretched. And we want to know, do we think there's a correlation between the number of weights and the stretch on the cord? Yeah, I'd say there is a pretty strong correlation because it looks just like a line right in there. So yeah, I'd say so. What do they ask me? They say, how would I describe the relationship? I'd say it's a pretty good fit. And yeah, pretty strong relationship there. Strong positive. So we would say that this R value is very close, and our R value is what we call a correlation coefficient, and we would say that this R value, the closer it gets to 1 or -1, the stronger that relationship is. If R happens to equal 0, then there is absolutely no relationship at all. So I would say that there was a very strong relationship for our data here. I would say it would be close to a 1. If it was going downhill, it would probably be close, it would be the negative relationship or the -1 relationship, and that's how those R values are formed. We don't have to do the computation for those anymore. We just enter our data and the calculator gives us those values. Inferential statistics means that you're going to take, and here we are, we're going to take a big group of people, and we want to say like all the people in America, or we've sampled a selection of people in America, and we say that Americans think a certain way. We think a certain way on a particular topic. Well, we're not going to go and sample every single American. So instead, what we do is get a sample of that population, and we try to get a sample that is representative of Americans. So we don't just go to the Republican Party headquarters and just poll those people. We want to poll people from a variety of places so that we can be confident in what we might say Americans are thinking. So and seeing as we have to make decisions about this, we can also say that statistics is kind of a fuzzy math, and I could make the data say what I wanted it to say just by polling in particular locations. So you have to be very careful with inferential statistics. Just because one person said Americans think one way, we could do another study and find something totally different. So we are trying to get what they call a convenience sample, meaning that we can't ask every single person to figure out what the majority of Americans think. We just can't poll all Americans. So we get, say, what's called a stratified random sample. And so, example of this, if we're going to be surveying students on campus, and we're wanting to be making some sort of assumption about what the students on campus think, and if 25% of the students are married, we want to make sure that we sample at least 25 or right at 25% of the students that are married, so it will be representative. Same situation whenever we are considering race. We want to make sure that these proportions are the same. Weighted averages, that's how we get our grades. That's something well, let's just go ahead and calculate some weighted averages and see what this means. It's kind of like a frequency chart as well. So if we look at this particular chart, now I don't know why they asked this one, because this doesn't even make sense that they asked this one. If all of these courses are 3 credits, then they're all weighted the same, and you could just get the average of this without even messing with the credits. So I'm going to change their question just a little bit. I'm going to say that this math course is a 4-credit class, just so that we can see what to do when it's not the same. So what you would do is you would take your B, which is worth 3 points, and multiply by its weight, plus the A, which is worth 4 points, multiply it by what its weight is. C is 2 points, and it's worth 3. And we've got another A, which is 4 points, and it's worth 3. Then we're going to take this, and we're going to divide it by whatever this total is. So however it's weighted, so that's 4, that's 10, 13. So we're going to divide by 13 here, and we're going to get our grade point average. So let me do that. Okay, let's notice the difference here. What's going on. I went ahead and did it for all 3 credit courses. So if they were all 3 credit courses, then you would just multiply and divide by the 12, and that would be your grade point average. But notice how with math being a 4-credit class, that brings down your grade point average just a little bit, because you have 4, it's the same as having 4 B's here instead of 3. So it brought the grade point average down just a little bit because that B was weighted heavier. So let's see what we have next. It says we've got to have a 2.5, and Amy needs to bring her grade point average up. Sometimes that happens at the beginning. She wasn't as dedicated, and now she decides she's going to be dedicated. So she's got to figure out what does she need to make in order to get this 2.5. Well, 50 credits times the 2.35 will be exactly what she's got, and let's see what she needs is going to be the 66 times the 2.5. So this is what she has. This is what she needs. So let me compute that for you. Okay, I did that computation for you, and let's get my pen back here. Want my pen back. Okay, so she has 117.5 points. What she needs after she takes those extra 16 credits is she needs 165 points. So what I did was I said 165 minus 117.5 was 47.5 is what she needs. She needs this to average out and get her 47. So I need 16 times that number. Let's just call it X, I guess. 16 times that number better be 47.5. So then I divided both sides by 16 to solve that equation, and then I got that X needs to be 2.96875. So I imagine she better make all B's or above. That's what she needs to get that 2.5 GPA. So she's going to have to study. All right. Well, that is the end of 7.2. If you guys have any questions, you be sure and send me an email. That's the best way to get a hold of me, is please send me an email. And I know that if any of you need any extra time on assignments, I know some of you have requested that, be sure and send me an email and tell me a proposed due date. And I'll see what I can do to grant that for you. All right. Well, you guys have a great day. Bye now.